Hello and welcome to my channel. Today I'm going to be addressing a topic that I have avoided for quite some time now, but I just can't ignore it any longer. Today in 2025, we find ourselves facing a crisis in the field of science and mathematics that has generally gone unnoticed. A crisis so severe that I have decided to make a special cameo appearance to drive the point home. But before we get too serious and gloomy, let's first start off by playing a game. The rules of this game are very simple. I'll flash the word of a color. Your challenge is to state the color of the font. In other words, state the color the word is printed in. Here's an example. If I display this word, which happens to read yellow, then you are to simply say black because the word is written in the color black. Okay? So now I'm going to display 10 colors in a row. Are you ready? Go. Okay, how did you do? Not too well, huh? But that's okay. This was your first time trying and I caught you by surprise, so let's try again. Ready? Go. Now, if you're like most adults, you did fairly poorly on this test. No matter how hard you tried to fight it, your brain kept telling your mouth to say the word instead of its font color. There's actually a term for this, and it's called the Stroop Effect. There's something similar to this effect in psychiatry called an aphasia. It goes something like this. A doctor could hand his patient an apple and ask the patient, "What's his color?" And the patient would say red. And then the doctor would ask, "If you bit into it, what would be the color of his flesh?" And the patient would say white. And then the doctor asked, "Does it grow on a vine or a tree?" And the patient would say, "A tree." And the doctor then asked, "Who ate this first, Adam or Eve?" And the patient would say, "Eve." And finally, the doctor would ask, "So what's his name?" And the patient would respond, "A pear." And then the doctor asks, "Don't you mean an apple?" And the patient responds, "Yes, that's what I just said, a pear." It's found that the people who tend to do best on these Stroop tests are kids who haven't learned how to read or at least read well, which makes perfect sense. The written word has no meaning to them and their brains only register the color of the font. But let's test to see if this is true or not. Once again, only state the color of the font. Ready? Go. Okay, how did you do this time? Better? I chose Sanskrit as the language hoping it would be sufficiently obscure enough so that most people wouldn't recognize it or be able to read it. Now, what was the point of all of this? Simply to illustrate that no matter how well you think you may have trained your mind, it still has a mind of its own, which segues nicely into our next topic. Here we see a gathering of some of the most wealthiest and powerful and most intellectually gifted people on the planet. This collection of individuals is called World Minds. They are an invitation-only organization made up of 1,500 members. They come from a wide range of countries and have made proven contributions in the field of science, the arts, government, and business. Their goal is, and I quote, "to improve the quality of our decisions as private individuals and as citizens of this planet." But perhaps most importantly, their charter limits the number of business members to 500 globally. It also stipulates that at least 51% of their community members have to be scientists. This is their way of ensuring that the group never devolves into a business club. And so we are forced to ask, why would people of such wealth and power band together to form this group? These World Mind members are literally the world's elite, the movers and shakers of world governments and industries. Many are also members of the WEF, so why this double dipping? What can World Minds do that WEF can't? Well, I humbly submit that they saw what I saw, an uneasy observation that I have reluctantly had to come to grips with over the course of several years. Academia, particularly in the fields of theoretical mathematics, theoretical physics, and in some branches of medicine, are slowly devolving into corporate proxies. Proxies who are in the process of losing both their objectivity and ethical moorings. They are falling further and further behind the emerging might of AI, making themselves slowly obsolete. This in turn is creating a whole new generation of young mathematicians and scientists who will also be made obsolete. Let me give you an example. These are key punch operators. During the 60s and 70s, key punch operator was one of the most advertised and sought after jobs in the want ads. Today we would list them as nostalgic relics of the past. These are 2024-2025 computer programmers. Almost overnight, they have become as plentiful and as unemployed as that 70s key punch operator. And unless and until they pivot and find a new specialty, they will become every bit as nostalgic as those key punch operators. Now I realize I may be sounding overly pessimistic, and I want to make it clear that I do not think this impending disaster has spread throughout all of the sciences and all of its branches. In fact, disciplines like computer science, genomics, and molecular biology are booming. Their success has been at an almost exponential rate, but the boom in computer science is due in part to making its processes more efficient by using AI, which ironically has led to more unemployment of human programmers. Sadly, some areas of theoretical physics, such as particle physics and especially quantum mechanics, has hit a brick wall. It has painted itself into a corner that it can't seem to get itself out of. Let me give you an example. If quantum mechanics physicists truly believe Heisenberg's uncertainty principle, then they would have to admit that not only does quantum mechanics nullify Newtonian calculus by eliminating the infinitesimal, but quantum mechanics would eliminate mathematics as we know it, including probability theory, the very theory upon which quantum mechanics is based. Once we pass that subatomic limit, all things classical become potentially wrong. But remember, the mathematics that we commonly employ is defined classically. Pure mathematics has been the standard for rigor and stability, yet the very foundation upon which calculus stands is faulty to a point where deeper insight into the field has essentially been halted. These foundations are in such a state of disarray and brokenness that it will take a Herculean effort to right the ship once again. And that, ladies and gentlemen, is where quick or Quaternionic or Eulerian Calculus comes to the rescue. Now once again I realize that for me to say quantum mechanics says that arithmetic fails at subatomic distances sounds crazy. But think about it. The Heisenberg uncertainty principle says 5 might be 5 or 4 or 7 or 700 because past a set limit they are, well, uncertain. And constants such as e, pi, and I cannot exist as constants. But if you think I'm being overly dramatic or just out and out making stuff up, let's see what TechLead has to say on the subject.
You are competing at the lowest common bottom denominator as far as standard of living goes with the cheap foreign immigrant labor, H-1Bs, with the AI bots. Everyone here to take your job, everyone can code. Even if we were to get this whole immigration thing under control, we are in an increasingly globalizing world with geo-arbitrage of labor. And so companies are still always going to find ways to outsource, to hire remotely, to just shift jobs overseas. They can open up foreign offices and branches. And even if you were to finally land that dream tech job, well then what? It's 80-hour grueling weeks of brutal dog-eat-dog grind. Who wants to sign up for this? And I covered this topic, the H-1B issue, multiple times, at least 3 times 4 years ago. And nothing happened, and it continues to today. I covered the STEM degree scam, I covered why coding is dead multiple times, and all you guys did, every time I meet one of you guys, you're a programmer. It's like, hey, I'm learning to code. Oh yeah, I'm a programmer. I always ask that question because I'm trying to figure out how many people are actually listening. And if you're not listening and you're continuing to be a programmer, then don't talk to me. How can I make this more clear? Why are you talking to me when I'm asking you not to do that and you continue to do it? And then you try to talk to me. Stop it.
Now many of you will dismiss TechLead for various reasons, and that's okay. Well, how about Sabine Hossenfelder? She has impeccable credentials. Let's see what she has to say on the subject.
I've been worried about the problem with academic research ever since I became part of it about 20 years ago. I didn't accidentally say that I became part of the problem because that's exactly what happened. Then, about 10 years ago, I wrote a book about what's going wrong in my own research area, the foundations of physics. But I'm afraid that the problem also befalls other disciplines. It's a failure of science to self-correct. Science is failing. It's failing failing right in front of our eyes and no one's doing anything about it. I think these past 50 years will go down as one of the most embarrassing episodes in the history of science. I can't stop physicists from continuing this insanity, but I can distance myself from it and I can draw attention to the problem, and that's what I'm doing. The reason this worries me so much is that I think this is a systemic problem caused by the way we organize academic research. This means it can happen in other disciplines and probably does happen. This is why I don't trust scientists. I can't, because I've seen in my own field that thousands of them might pursue for decades what's obviously pseudoscience. Or take this quote from a recent opinion piece by William Deresiewicz in the Chronicles of Higher Education, where he writes about the humanities. Those fields have another thing in common. They're intellectually corrupt. You know what I'm talking about. Any fool idea passes muster, no matter how preposterous, as long as it conforms to prevailing theoretical trends and preferred ideological positions. Nobody wants to make waves, to speak up at a conference, to undermine a colleague or colleague student, to invite examination of their own research. Data is massaged, texts are squeezed or bound and gagged. Jargon helps to paper over cracks in logic. Countervailing evidence is tucked under the cushions. In the foundations of physics, the problem presents itself differently. It's not that they ignore evidence, it's that they figured it's easier to publish theories for which there is no evidence. In the life sciences, we see research bubbles built on shaky evidence that no one wants to question. In the social sciences, psychology and public health, we have p-hackers and post-selectors. In some parts of biomedicine and material science, we have an entire industry cranking out scam papers that no one reads, and so on. It looks different in each field, but these are all symptoms of the same underlying problem. Researchers in academia don't get paid for being useful. They get paid so long as other people in academia approve. It's a self-optimizing system, yes, but what it optimizes is how to please other academics with the least amount of effort.
Okay, many of you will dismiss her too because she left the world of academia and Professor Dave told you not to take her seriously. So how about Leonard Susskind?
Look, there are still people who believe in the flat earth, for God's sakes. There's people who believe all kinds of weird stuff. Don't think about individuals. Think about the consensus of the largest fraction of physicists working on these things, and you'll probably be right. The overall consensus of the field tends to be right. The peculiar individuals, no matter how famous they are, no matter how brilliant they are, if they're off that consensus, and they've been off that consensus for a long time, they're probably wrong. That doesn't mean for sure that they're wrong. But don't look for the weirdos. Look for what the consensus of, the majority of well-respected, highly accomplished physicists believe. And you'll probably be right. They'll probably be right. There's no guarantee of it. There are very few cases where the consensus has gone wrong for a long period of time, just where some offbeat idea of some particular individual suddenly changes everything. I'm not saying it doesn't happen, but rarely. So Penrose, what can I say? He believes all kinds of things that I don't that I wouldn't subscribe to. But more than that, things that the consensus wouldn't subscribe to.
Now,
South Northern April of 142!
But you're perfectly right. We should certainly be on the lookout for ideas which are not the consensus. We should be watching for them and not immediately dismiss them because they're not exactly the same as the ideas that we've been pursuing. For sure, we should be doing that. So I would agree with you about that. Look, you're right. Most of the people I know, and that might even include myself to some extent, are a little bit are derisive about a lot of these ideas. And you're correct that that there is a very strong skepticism about them, and maybe to some extent unfounded. We all know that there's nothing hidden about that. So think for yourself. Don't pay any attention to people who say something is impossible if you think it's possible, and that's my main. And be curious. Well, don't be afraid. Don't be afraid. Follow your curiosity. If your curiosity goes in some other direction than the direction that the current consensus is pursuing, don't be afraid to pursue it. So think for yourself. Think for yourself, and don't be afraid to pursue it and follow your curiosity. That's my. And if you don't think you can do that, you're probably in the wrong field.
But let's face it, no matter who I put forward to plead this case, you're still going to dismiss whatever it is they have to say due to a type of overwhelming academic Stroop effect. Not only will you not believe it, but you can't even entertain it. Your brain just will not allow it. Cognitive dissonance at its finest. Weilberger very politely calls it the sociology of pure mathematics. Next time any of you submit a paper to a journal, pay particular attention to one of the first questions you are required to answer. How would you like to be addressed? Dr., Mrs., Ms., Mr. Now what do you think happens to those entries that are labeled anything other than doctor? Okay, no more speculations and conspiracy theories. Let me get off my soapbox and let's get down to business. Let me give you a real-world example. One of the most famous conjectures of all time was Fermat's last theorem. Fermat stated that no three positive integers, a, b, and c, can satisfy the equation a to the n plus b to the n equals c to the n for any positive integer value of n greater than 2. In 1993, Andrew Wiles proved that Fermat's last theorem was true. He was awarded the Abel Prize, which is kind of like the Nobel Prize of Mathematics, and was knighted for his outstanding achievement. I arrived on the scene several years later and discovered Johnson's theorem. Johnson's theorem essentially says that Fermat's last theorem is false. Now I realize such a proclamation immediately places me at the top of the crackpot list. Practically everybody listening to this video is saying I'm nuts, and there's no need to hear any proof I may have to offer, and this immediate rejection is perfectly understandable and predictable. But please just bear with me a bit longer. My proof of the negation is ridiculously brief. Just 3 short steps. It is truly in fact a margin proof. So brief you could place it in a margin of a book. Now here's the proof. Now after reading the last line of this 3-step proof, the Stroop effect immediately sets in and takes effect. Any high schooler who has taken a course in exponents will tell you the proof is correct. There's nothing complicated about it. In fact, it is almost too simple to be believed. But all of you who have had extensive training in mathematics knows beyond a shadow of a doubt that it's wrong. And why is it wrong? It's wrong because, well, it just has to be wrong. If it were this simple, mathematicians way smarter than me would have discovered it centuries ago, right? Now at this stage, I'm not going to try to convince you the proof is correct. It would just be a waste of time. The power of the Stroop effect is just too powerful right now. But don't worry, we will revisit this proof later on in the video. And while we are here, I may as well prove the Bill conjecture. And once again, you're not going to believe this proof unless you believe Johnson's theorem is true and Fermat's last theorem is false. So let's just move on. But before we move on, let me make it perfectly clear that I am in no way trying to discredit the work of Andrew Wiles. But what I am saying is that Johnson's theorem is true. Believe it or not, my primary aim is not to preach against the shortcomings of academia and scientists and big bad tech. My overarching aim is to introduce to as wide an audience as possible the wonders and usefulness of QEC. But given the existence of this intellectual Stroop effect, selling QEC to the scientific world is going to be an uphill battle, to which the most clever of you will say, wait for it. But let's hear what Peter White has to say.
The history of it, yeah, so this was often attributed to Pauli, that it was something that he was known to be very critical of things and to say, oh, you know, at a talk, this is wrong, this is completely wrong. And supposedly late in life, he was asked by somebody about some paper and he shook his head and said, oh, well, that one's not even wrong. And you could take it as, you know, a really somewhat nasty and aggressive put down is that's so bad it's not even wrong. But there's also another meaning to me has always been that, you know, whenever people are working on speculative ideas, you know, they're always not clear whether they're right or wrong. And then the whole point of the thing is, you know, how do you get some idea to the point where you can tell whether it's right or wrong? And so not even wrong also kind of applies to, you know, most of my own work or most of what everybody is doing in this subject, and how you kind of, you know, anyway, how you emerge from that into something which can be right or wrong is not so clear.
Well, given that point of view, then I'm fairly confident that QEC will eventually catch on. Eventually, one way or the other, mathematicians and scientists have got to come back to QEC, even if they have to buy high. Now, what is QEC? QEC is Quaternionic Eulerian Calculus. It is a system of integral and differential calculus based exclusively upon Euler's formula. But so what? What is it about QEC that makes it so much more attractive or a more useful system than, say, Leibniz or Newtonian calculus? Well, the primary reason is that QEC is logically consistent and makes so much more sense algebraically. Newtonian calculus does not. Newtonian calculus is based upon the Newtonian limit, and the Newtonian limit is seriously flawed. The concept of the infinitesimal and the notion that the slope of the y-axis is undefined are nonsense and have no place in QEC. There is yet to be any proponent of Newtonian calculus who has convincingly refuted the arguments of Bishop George Berkeley. Mathematicians have simply chosen to just ignore his objections. Berkeley, like many of us who have actually tried to grasp the Newtonian limit, all freely admit that the Newtonian limit stumbles its way into getting the correct results. But the process it uses to get those results is mathematically untenable. You just can't mathematically do what your professors and teachers tell you to do in order to compute the limit, and no amount of delta epsilon proofing is going to change that fact. Ultimately, the fatal flaw in the theoretical underpinnings of the Newtonian limit is their covert employment of division by zero. The founders knew this was not allowed, so they invented all kinds of tricks and abracadabra to mask it. This is why today your instructors tell you that the slope of y is undefined, because to do otherwise would mean division by zero, but will simultaneously tell you that the slope is a precise y value. But what about when you're told that you shouldn't regard dy over dx as a fraction, because if x is 0, then the slope becomes undefined, while simultaneously being taught that dy over dx is a rate, which is a fraction. This is the illogical corner Leibniz and Newtonian calculus has painted itself into. Students struggle learning calculus in the beginning stages because its theoretical underpinnings are flawed and make no logical sense. On the other hand, QEC is student-friendly. It is quintessentially algebraic and is based upon the logic of algebra, so students shouldn't have any problems grasping the theories of QEC. So let's get started by presenting the fundamental equations of QEC. These two equations form two of the three fundamental pillars upon which the whole of trigonometry, calculus, and QEC rests. The third pillar is Quaternion algebra, where I equals jk. These equations form the whole of Quaternion algebra and trigonometry, which forms the whole of QEC. So we just established the algebra of QEC, but what exactly is a quaternion? Well, it turns out that a quaternion can be expressed in a wide variety of ways, but for right now we like to think of a quaternion as being both an arc length and a trigonometric identity, and we measure arc length in radians. We round out these definitions with the Quaternion rotation formulas. Rotation in the plane reduces to the simple multiplication of complex numbers. Complex number multiplication is commutative, so we can multiply them in any order we wish. So we get an equation that looks something like this. And doing the necessary algebra, we wind up with an equation that says q prime is equal to e to the theta I times q. Therefore, e to the theta I will rotate any vector q in the complex plane theta radians. But remember, all vectors are quaternions, and I will rotate any quaternion pi over 2 radians. When we want to rotate a quaternion or vector in three-dimensional space, or for our purposes around the unit sphere, we have to extend the unit vector out of the plane. The equation looks just like multiplying complex numbers. But remember, a complex number is still a quaternion, so there should be a general formula that can be applied to all quaternions that exist in any of the 4 dimensions. To do this, we can take the e to the I theta of complex multiplication and divide it into its 2 component parts. Now in quaternion multiplication, the order of multiplication actually does matter because quaternion multiplication does not commute. But what all this demonstrates is that quaternions act as if they are spinning tops or gyroscopes. And one of the best ways to get a mathematical handle on them is to apply the laws and principles of gyrodynamics to them. Anyway, by allowing the quaternion to wobble or precess, we are able to rotate quaternions in 3 dimensions. And we can express this precession in our complex number multiplication equation by introducing opposite spin. We can do that by flipping the order of the 2 quaternions. And this gives us the Quaternion rotation formula, or the Quaternion rotator. We first begin by drawing a circle. We place a point at its center called the origin. The origin is always designated as being 0. In QEC, 0 is never null. There is only the 100% absence of something that is always replaced by 100% of its conjugate. Consider a conjugate as being an extreme. We next place the derivative of Euler's constant e to the 1 at the origin. Extending right, we then extend e from the origin to its outermost extreme, the intersection of the x-axis with the circumference. At the circumference, e forms its conjugate e star, where e star equals e to the 0 equals 1. Therefore, e star forms a radius of 1. Since e is self-conjugate, then at the circumference, e forms a double point. Starting from the left, we extend e from the center to the circumference. This forms the cosine. Starting from the right, we extend the conjugate of e, e star, from the circumference to the center origin. This forms the versine, where the versine is defined as the versine is equal to the sagitta equals 1 minus the cosine. A fully extended cosine and a fully extended versine spanning the space from center to circumference both form radii of 1. E may matriculate to any point within or upon the unit circle. We allow E to traverse along the circumference some radian arc length. And any such radian arc length, no matter its magnitude, is a quaternion. Therefore, any point along the circumference is a quaternion, as well as any 2 pi radian circle, as well as any object that may be measured in radians or degrees. Therefore, all platonic solids, conic sections, and any geometrical element constructed from these constructs may all be designated as quaternions. From some point along the circumference, we construct a normal extending from the point to the x-axis. This is the sine. From the origin, proceeding to the right, we draw a line perpendicular to the sine along the x-axis until this line intercepts the sine. This is the cosine. From the circumference, proceeding to the left, We draw a line perpendicular to the sine along the x-axis until this line intercepts the sine. This is the sagittal. The sagittal and the versine are identical, except the relationship of cosine to versine is horizontal, and the relationship of the sine to sagittal is orthogonal. The versine and sagittal occupy the exact same space. The sine and cosine form a right triangle. The hypotenuse of this right triangle is the tangent. The sine and sagittal form a right triangle. The hypotenuse of this right triangle is the secant. The secant forms a chord which defines the extremes of the quaternion arc length, which by definition is a quaternion. From the list of trigonometric identities, I is always perpendicular to the tangent. Several operations occur in the QECian unit circle acting synergistically and simultaneously. All processes begin at 0 degrees or 0 radians. They reverse at 180 degrees or pi radians. They then repeat at 360 degrees or 2 pi radian. Let's focus our attention on the unit radius, which is labeled as the black tangent. As the tangent revolves or precesses about the unit circle, its length always remains constant. Let's next focus on the red sine. Pay particular attention to its extreme ends. The sine grows from 0 at 0 degrees or 0 radians to a maximum length of 1 at 90 degrees or pi over 2 radians and returns to a value of 0 at 180 degrees or pi radians. The sine immediately reverses its direction of growth and once again reaches a maximum of 1 at 270 degrees or 3/2 pi radians, returning to a value of 0 at 360 degrees or 2 pi radians. The upper extreme of the sine accelerates and precesses along the circumference, while rectilinearly and simultaneously, the lower end of the sine accelerates along the x-axis. As the red sine accelerates across the x-axis, the versine increases in value while the cosine simultaneously decreases in value. When the sine reverses its direction of travel, going from left to right, then it is the versine that decreases in value as the cosine gains in value. Next, focus on the growth of the arc length or quaternion. As the tangent precesses about the circle, it grows the red quaternion. The same can be said of the sine. The red sine grows the red quaternion incrementally, forming the red circumference. Where the black tangent always remains constant, the green secant is constantly changing. At 0 degrees or 0 radians, it grows from 0 to a maximum length of 2 at 180 degrees or pi radians. It immediately reverses its direction of growth and once again reaches a minimum of 0 at 360 degrees or 2 pi radians. The red tangent, as I, is always perpendicular to the constant black tangent. In QEC, we will often designate the hypotenuse as being the tangent. However, the hypotenuse should technically be designated as the tangent line. Any and every point along the tangent line as hypotenuse is technically a tangent point. Therefore, a tangent line is a summation or concatenation of an infinite series of tangent points or tangents or tangent locations that sum or concatenate to form the tangent line as hypotenuse. The tangent is also defined as being a slope. A slope is the rate or fraction or quotient or ratio of a y value over an x value. Therefore, any and every point along the tangent line must be equivalent, since any and every point must have the same y over x value. Therefore, any and every tangent point that lies along or upon a given tangent line is equal. The arc length may be considered as a summation or concatenation of an infinite series of points or e's or e locations as e propagates along the circumference. Since the secant is a hypotenuse and every point along the hypotenuse must be equivalent, then the chord is a quaternion since every point along the arc length is a quaternion, since e is a quaternion. And since by the Pythagorean theorem, the secant is the sum of the sagittal and the sine, then the sagittal and the sine must be quaternions. Given the trigonometric identities, then the rate of the sine of the sagittal forms a hypotenuse, which is the secant. Therefore, the secant is a quaternion. And just as with the tangent, every point along the secant is a quaternion. And since the unit sagittal and unit cosine span the exact same length, then the sagittal and cosine must be quaternions. And given the Pythagorean theorem, where the sum of the sine and the cosine equals the tangent, then the tangent must be a quaternion. And since all trigonometric functions may be defined in terms of the sine, cosine, and tangent, then all trigonometric functions and their identities are quaternions. And since E occupies a point on the circumference, then E and its conjugate are both quaternions, no matter their location. Therefore, any and every point within or upon the unit circle is self-conjugate E. Therefore, any and every point that lies within or upon the unit circle is a quaternion. Therefore, E, E star, I, pi, theta, 1, and 0 are all quaternions. Therefore, any and every point that lies within or upon the unit circle is a self-conjugate double point. Therefore, since any and every point within or upon the unit circle is equivalent to self-conjugate E, then any and every point within and upon the QECian unit circle must obey Euler's formula. Here we see before us one of the most fundamental rules of QEC. Let's quickly prove this. In the unit circle, the x-axis diameter has an absolute value of 2, and the y-axis diameter has an absolute value of 2i. Half of the x-axis is 1, which places you at the origin. Half of the y-axis is I, which places you also at the origin. The origin forms the midpoint, or half of both diameters. Therefore, plus or minus 1 equals plus or minus 0 equals plus or minus I equals plus or minus the square root of negative 1, which equals plus or minus 1/2. In QEC, a negative sign means take the reciprocal of. Therefore, I equals negative 1/2 equals 2. More on this later. Therefore, we can finally say plus or minus 1 equals plus or minus 0 equals plus or minus I equals plus or minus the square root of negative 1 equals plus or minus 1/2, which equals minus plus 2. Now from this illustration, we see that when the cosine is 0, then e to the x equals e to the 0 equals 1. And from this illustration, we see that by sliding this right triangle with a constant base of 1 up and down the x-axis, we are always able to compute the slope simply by measuring the height of e to the x. This illustration gives us a beautiful consolidation of quaternionic orientation and their trigonometric properties. We can actually consolidate the two illustrations. The height of e to the x still equals e and corresponds trigonometrically to the tangent. But note that it always lies along the hypotenuse or slope formed by the unit radius of 1, which is always a tangent. Any and every point lying along the hypotenuse must possess a slope or tangent of 1. E lies along this slope, so therefore as tangent, it must also have a value of 1 within the unit circle. And so the unit radius of Euler's formula is actually E. Therefore, plus or minus 1 equals plus or minus 0 equals plus or minus I equals plus or minus the square root of negative 1 equals plus or minus 1/2 equals minus plus 2 equals E. We can now interpret the Quaternion Rotator as saying E intercepts the circumference at point Q. I intercepts E at a right angle and rotates E theta radians to the final destination, point Q prime. But from this illustration, we see that the constant one-base triangle also dictates the value of phi to the x. This must be the case because there must be some value of x where e to the x equals phi. Therefore, phi and e are both defined by exactly the same curve. Therefore, the slope of phi is simply the height measured along the height of e, where e is equal to the tangent. Notice that phi squared as hypotenuse is the quadrants of the height phi. Quadrants is the square of length, and in QEC, quadrants and length are equivalent in a right triangle, and this we'll prove later. Therefore, phi is indeed equivalent to phi squared. This also means that it forms a tangent point along the unit radius hypotenuse. Therefore, this would yield the final result of plus or minus 1 equals plus or minus 0 equals plus or minus I equals plus or minus the square root of negative 1 equals plus or minus 1/2 equals minus plus 2 equals E equals phi. This we can also prove algebraically. Keep in mind, since we are treating phi as a quaternion, it therefore acts as a slope. So 1 is the slope of phi and not its magnitude. Finally, the illustration implies that there are 3 special ratios that occur: cosine to versine, cosine to cotangent, and cotangent to sine. One of these special ratios must correspond to phi. However, in QEC, the slope of y is 1. You can see from the illustration that the height of I, which is the same as y, meets the hypotenuse and therefore must have a slope of 1. We can very easily prove that all quaternions are natural logs. Let's take e to the I theta. The natural log I represents any unit quaternion, and the natural log theta represents any quaternion, since a quaternion by definition is an arc length. Therefore, all quaternions are natural logs, and as such, must obey all the rules of natural logs. Since quaternions act as natural logs, this is simply an expression of the power rule for exponents. In fact, we call it the QECian power rule. More on this later, too. Every quaternion may be expressed as a slope or a ratio of some two trigonometric identities. Every quaternion may also be expressed as the product of some two trigonometric identities. This is also the case for trigonometric identities. Therefore, all trigonometric identities are quaternions. Also notice that the cosine, cotangent, and sine are equivalent. The sine, 1, and tangent are equivalent, and 1, the cosecant, and secant are equivalent. We may abbreviate Euler's formula to read as Q equals A times e to the I theta, where Q is a quaternion and A is called a tensor. A tensor is a dimensionless factor of the unit quaternion, and the unit quaternion is cosine theta plus var epsilon sine theta. The tensor A determines how many full 2 pi revolutions the unit quaternion executes. The unit quaternion must obligatorily equal 1, so A must obligatorily be some integer. Therefore, all integers must be a quaternion. The implications of this is that projective geometry and Norman Wildberger's universal hyperbolic geometry are alternative expressions of quaternion algebra. There are two words we use a lot in QEC, and that is fungibility and equivalent. QEC is based upon the behavior of the unit quaternion within and upon the unit sphere. One unit quaternion is no different than any other unit quaternion. They are all equivalent. In this equation, A and e to the I theta are fully equivalent. I is equivalent to J, is equivalent to K, is equivalent to I. This is why all trigonometric identities are equivalent. Since they are equivalent, we must be able to navigate from one quaternion to the next seamlessly, no matter what form each respective quaternion takes. This is why we can seamlessly transition from the irrationals of e to phi to I to the rationals of 1 to 2 to 1/2. We have spent a considerable amount of time establishing the foundations of QEC. We are now able to finally explore how QEC actually works. In QEC, we compute the derivative in 4 different but equivalent ways. Let's get started with the difference quotient. In order to really appreciate how QEC functions, we have to understand how the quaternion, as a trigonometric identity, operates within the unit circle. From the animation, we see that when the cosine obtains a value of 0, then the versine obtains a value of 1, and vice versa, or in other words, the cosine plus the versine equals 1. This is perhaps the most seminal operating principle in QEC. When a quaternion, as a trigonometric identity, obtains a value of 0, we obligatorily obtain 100% of its reciprocal or conjugate. Let's put this principle into practice and derive the QECian difference quotient and the QECian limit. However, before we do that, let's first see how the Newtonian limit is derived, and for that we shall use the talents of several well-known internet instructors. Now, I want to make it perfectly clear that I am in no way criticizing these instructors. I chose these tutors at random because this is the standard procedure that has been used for centuries to teach the derivation of the Newtonian limit, and I wanted to establish that this is the standard way of teaching the limit in most high schools and universities. But I want you to concentrate on how they all perform this curious operation of canceling h's.
Now, how do you simplify this? I could say this is equal to the limit as h goes to 0. I'm going to pull out an h from the top. It's going to be h inside minus 2. All I did was factor out an h, and this is over an h. Now, the only reason I really did that is because I knew that if I did that, this would cancel with this. Okay, because h divided by h is 1. So in the end, I'm going to be left with limit as h goes to 0 of the quantity h minus 2. Now here's where you can apply what I showed you just a minute ago. Here I'm taking the limit of this function, h minus 2, as h goes to 0. So what do? You just plug in 0. Okay? You put 0 in here, and then whatever you're left with is the answer, -2.
The 3's cancel, and we're left with 2hx plus h squared divided by h. We could factor out an h, so we have 2x plus h divided by h. The h's cancel. This is our final result, but if we want to take the limit as h approaches 0, we can substitute 0 in for h here, and we're going to get 2x.
It is perfectly legitimate to cancel out a pair of h's in the numerator and denominator, provided h does not equal 0. But as one of the instructors clearly indicates, this is not the case. H cannot equal 0 if you are using the difference quotient to compute the limit, at least not by Newtonian standards. Ignoring this fact, they cancel out a pair of h's anyway and then immediately set the remaining h to 0, which is still forbidden. The condition that h cannot equal 0 still holds throughout the entire process, and it is this illegitimate canceling of the h's that is the fatal flaw in the Newtonian limit. To illustrate this point, let's transition from the amazing animations of Becker's Animation Versus series and take a look at some of the amazing animations in Sanderson's 3 Blue, 1 Brown series.
There is a really nice visual understanding for what it means to ask what this ratio approaches. Remember, for any specific choice of dt, this ratio ds dt is the slope of a line passing through two separate points on the graph, right? Well, as dt approaches 0, and as those 2 points approach each other, the slope of the line approaches the slope of a line that's tangent to the graph at whatever point t we're looking at. So the true, honest-to-goodness, pure math derivative is not the rise over run slope between 2 nearby points on the graph. It's equal to the slope of a line tangent to the graph at a single point. Now, notice what I'm not saying. I am not saying that the derivative is whatever happens when dt is infinitely small, whatever that would mean. Nor am I saying that you plug in 0 for dt. This dt is always a finitely small, non-zero value. It's just that it approaches 0 is all. I think that's really clever. Even though change in an instant makes no sense, this idea of letting dt approach 0 is a really sneaky backdoor way to talk reasonably about the rate of change at a single point in time. Isn't that neat? It's kind of flirting with the paradox of change in an instant without ever needing to actually touch it. And it comes with such a nice visual intuition too, as the slope of a tangent line to a single point on the graph. And because change in an instant still makes no sense, I think it's healthiest for you to think of this slope not as some instantaneous rate of change, but instead as the best constant approximation for a rate of change around a point.
Sanderson comes real close to letting dt equal 0, which would be h in his difference quotient, but stops just shy of that step. Instead, he boldly announces that the Newtonian limit is really an extraordinarily good approximation, which is exactly the contention of Quick. Given the way the Newtonian proof is constructed, the Newtonian limit can only be a very good approximation. It can never be exact, because in order for it to be exact, h would have to equal 0, and this implies by Newtonian standards division by 0, which is forbidden. On the flip side, Newtonian calculus computes a derivative by the classic shrinking of the secant to its limit as a tangent, a process Quick enthusiastically supports. In Quick and in Newtonian calculus, we can dodge the fatal flaw of division by 0 by trigonometrically stating that when a single point of the secant coincides with a single point of the tangent, then we have reached the limit. Now let's switch over to the QECian derivation. Quick utilizes the difference quotient to find the limit just like the Newtonian limit does, except with one small but seismic change. H must precisely equal 0. Remember this equation? Well, in Quick, the sine and cosine are opposites or conjugates. So this equation means that when x equals 0, then its opposite or conjugate must automatically equal 1. So we apply this to the difference quotient and derive the QECian limit. And we can prove this quite easily. In the unit circle, as we advance the unit radius around the unit circle, the cosine diminishes while the versine, which is the negative cosine, grows. At pi over 2 radians, the cosine becomes 0, while simultaneously both the sine and versine become 1, because the versine equals minus cosine, which equals minus x, which equals 1. Remember, in Quick, the sine is y and the cosine is x. So given the QECian limit, then we simply get 0 plus 0 over 1 equals 0.
And importantly, those approximations get more and more accurate for smaller and smaller choices of dx, right? So this ratio, negative pi over 2, actually tells us the precise limiting value as x approaches 1. And remember, what that means is that the limiting height on our original graph is evidently exactly negative pi over 2. Now, what happened there is a little subtle, so I want to go through it again, but this time a little more generally. Instead of these two specific functions, which are both equal to 0 at x equals 1, think of any two functions, f of x and g of x, which are both 0 at some common value, x equals a. The only constraint is that these have to be functions where you're able to take a derivative of them at x equals a, which means that they each basically look like a line when you zoom in close enough to that value. Now, even though you can't compute f divided by g at this treble point, since both of them equal 0, you can ask about this ratio for values of x really, really close to a, the limit as x approaches a. And it's helpful to think of those nearby inputs as just a tiny nudge, dx, away from a. The value of f at that nudged point is approximately its derivative, df over dx, evaluated at a times dx. Likewise, the value of g at that nudged point is approximately the derivative of g, evaluated at a, times dx. So near that treble point, the ratio between the outputs of f and g is actually about the same as the derivative of f at a times dx divided by the derivative of g at a times dx. Those dx's cancel out, so the ratio of f and g near a is about the same as the ratio between their derivatives. Because each of those approximations gets more and more accurate for smaller and smaller nudges, this ratio of derivatives gives the precise value for the limit. This is a really handy trick for computing a lot of limits. Whenever you come across some expression that seems to equal 0 divided by 0 when you plug in some particular input, just try taking the derivative of the top and bottom expressions and plugging in that same treble input. This clever trick is called L'Hopital's rule.
Let's delve a bit more into L'Hopital's rule. Sanderson says that this rule computes a precise value of the limit. Well, yes and no. The rule most certainly computes a precise value of the limit, but not by the mathematical precepts employed by Sanderson. Both Quick and Sanderson have proven that the Newtonian limit, as it stands, cannot compute an exact value, only an approximation, and it therefore cannot compute a precise limit or derivative. However, it is clear that the final precise value of the limit obtained via L'Hopital's rule is not a Newtonian limit, yet Sanderson computes it as such. Though the illustration is both captivating and illuminating, it still uses the discredited infinitesimal or nudge or better and better approximations in the form of his dx's to gain the final result. And so this treatment is no better than his approximations derived earlier for the Newtonian limit. His mathematical processes, as well as those applied by most other mathematicians and theorists, cannot account logically nor mathematically for the precision of the obtained limit. However, what L'Hopital's rule establishes most beautifully and definitively is that all quaternions are derivatives. L'Hopital's rule is essentially the QECian limit expressed as a quaternion. By taking the derivative of both numerator and denominator, you thereby form the quaternion gamma. Any and all quaternions must obey the QECian limit. When applying L'Hopital's rule, one interpretation we may use is that we are essentially shrinking a secant into a single point, that point being the tangent. That single point is the intersection or confluence of two oppositely advancing curves. In Quick, this common point of intersection represents what is known as the instantaneous center of revolution, or the ICR, and each of the two curves are classified as being a centroid. What L'Hopital's rule establishes secondarily is the existence and real-world applicability of the Eulerian fundamental theorem of calculus. At the ICR, the integral becomes indistinguishable from the derivative. In using L'Hopital's rule, the final form attained by the initial equation is a form known to be indeterminate, and of course this form would be considered as being indeterminate because it has a zero divisor, which is forbidden when applying Newtonian standards. But in quick, since the denominator is the conjugate of the numerator, then the denominator is, in effect, the antiderivative of the numerator. At the ICR, and thus at the limit, the antiderivative and the derivative, or f and f prime, become indistinguishable. And so we obtain the following equation, which becomes a perfect mathematical representation of the ICR. And since the ICR has been defined as being a precise limit without any mention or use of dy's or dx's, then L'Hopital's rule becomes a valuable and legitimate tool for evaluating precise limits. But e to the x also displays similar behavior since the derivative of e to the x equals e to the x. And so we could expand this definition of the ICR to be the following equation. And so in an attempt to provide a bit of intuition, we can consider the difference quotient as being a tangent that pokes a hole in a continuous or differentiable curve, and L'Hopital's rule as being mathematical snoop. Snoop is essentially a dilute soapy water solution that bubbles when it detects a hole in a gas line. L'Hopital's rule detects leaky continuous curves. It creates a quaternion at the precise location of the singular hole that exists in an otherwise continuous curve. L'Hopital's rule is essentially Chasles' theorem. Chasles' theorem basically says take any null point, which is any quaternion on the circumference, which may be any integer, and join it to some other four null points. This null point is represented by the Greek letter eta. The lines forming the four meets form a cross ratio no matter the location of eta on the circle. We may rotate eta however we please about the circumference of the circle, but its cross ratio remains invariant. The cross ratio is the mathematical genome of that quaternion and forms a unique derivative. Therefore, eta obeys the standard equation of quaternions. Therefore, the cross ratio is equal to a plus bi plus cj plus dk, thereby ensuring that all quaternions are four-dimensional. The sliding link represents a rigid body that slides down along the wall under the force of gravity, while simultaneously sliding across the floor. The motion of a rigid body can be considered as being equivalent to the rotation of that body about a fixed center in space. Why? Because the ends of the latter trace out exactly the motion of 2 points, one being the sine, which is the wall, and the other being the cosine, which is the floor, as the radius spins in the unit circle. That fixed center is the instantaneous center of rotation. The two circles rotate past each other in opposite directions, meeting in one single tangent point that must have a net velocity of 0. That single tangent point is the ICR. Once an instance of 0 velocity has passed, then the rigid body continues on to its next position, creating a new subsequent ICR. This means any centroid is composed of an infinite number of ICRs, all of which are tangent points, which means all of these ICRs are derivatives and therefore quaternions. The movement of the instantaneous center describes one curve in space called the space centroid and another curve within the body itself called the body centroid. By definition, the space centroid is the fixed centroid and the body centroid is the moving centroid. At the ICR, the space and body curves become indistinguishable from one another. Since the ICR is tangent to both curves, the ICR defines the slope of the curve's mutual tangent line. Therefore, the ICR is the derivative of both the space and body centroids, or it is the integral of both, or one of each. This is the essence of the Eulerian fundamental theorem of calculus, that at the ICR it becomes impossible to distinguish the integral from the derivative. The Eulerian fundamental theorem of calculus incorporates the Newtonian fundamental theorem of calculus that says integration and differentiation are mutually inverse processes. This QECian proof of the ICR being a limit and therefore a derivative is very similar to the proof used by L'Hopital. Where L'Hopital squeezes the secant between two curves, QEC squeezes any curve between the space and body centroids by using the squeeze theorem, and thereby proving that the common tangent point of all three curves equals a limit and therefore a derivative. In QEC, the Eulerian fundamental theorem of calculus allows us to interpret integration and differentiation as merely rotating or precessing a point about a unit circle. Arbitrarily rotating it forward to a final position is differentiation or precession, and rotating it in reverse to its original position is integration or rotation. Again, the direction of rotation is completely arbitrary as to which is integration and which is differentiation. Given our rotation formula, we can easily rearrange it to obtain a value for the slope and therefore the derivative. It also follows that given our rotation formula, that the derivative of q may be computed by simply rotating q via the Quaternion rotation equation to its final location, q prime. When unit quaternion concepts are applied to the difference quotient, the conjugate of h is defined as simply 1 over h. This is allowed since h is equal to the versine, which is equivalent to a versor. From this we can independently derive the Quaternion rotator. Since h and h star are reciprocals, then we get this equation. And since 1 is a constant, then we get the Quaternion rotator in antiderivative form. To find the derivative, we simply flip the h's. And from this derivative, we can create the Quaternion form of the derivative. And so in terms of quaternions, the derivative f prime of x is a Quaternion rotator that precesses the ICR along its space and body centroids h star and h. And so we obtain in its final form the Quaternion rotator acting as a type of differentiation machine. This proves that the rotator is the space and body centroids forming a common ICR. It also demonstrates that at the ICR the integral and derivative become indistinguishable. We earlier derived this form of the Quaternion rotator. 1 is the y-intercept, which means when x is 0, then y the slope equals 1. Therefore we prove once again that the slope of y is 1. Another somewhat unique method of finding the QECian derivative is employing a Fermatian integral or a Fermatian derivative. Again, at the ICR, the derivative and integral become indistinguishable. Fermat began with this simple problem. Given a line, divide it into 2 parts such that the product of the parts will be a maximum. His final result was 2a plus e equals b. And intuitively, knowing what the answer should be, he just arbitrarily made e 0 in the last equation and got a final answer of a equals 1/2 b. He knew that with this oddball procedure, he could also compute tangents to the curve as well. He was arguably the first to discover and use a difference quotient as a means of finding a limit. Him getting rid of e by making it 0 is just like those tutors getting rid of h in the denominator by illegitimately canceling out the h in the denominator. This has become a standard operating procedure because mathematicians have completely ignored what e and h actually are. E and h are at their most rudimentary line segments expressed as cosine. And what nobody seems to get is that calculus is very simply trigonometry. This is why everybody struggles with the inevitable division by 0. In Fermat's equation, e doesn't go to 0 algebraically, but rather e goes to 0 trigonometrically. And from this analysis, we can establish Fermat's rule. A half of any quantity is a derivative. Again, we can easily solve Fermat's problems by using QECian principles. The cosine and versine are conjugates. Whatever one function gains, it must gain from the other. Therefore, every gain produces an equal loss. That gain and loss is balanced only when both cosine and versine are equal. Therefore, when they are equal, a equals b minus a, and they reach this maximum at b over 2. Therefore, e equals x plus h. By suppressing e, that is to say as e goes to 0, the limit of f of a is obtained, and therefore the derivative f prime of a equals b over 2, and is derived exactly. This is called a Fermatian derivative. Of course, the Eulerian fundamental theorem of calculus demands that a Fermatian integral, which is a centroid, would therefore be found by simply adding the 2 parts, restoring the centroid to a value of 1. Remember, a centroid is a collection of at least 2 quaternions. Therefore, the integral equals 2a, which equals b. But the Eulerian fundamental theorem of calculus also says that 2a equals b could also be the derivative, or a minima, or a maxima. And so once again we confirm Fermat's rule. Classically in Newtonian Leibnizian calculus, the definite integral is introduced as the solution to finding the area under a curve. It is presented as the limit of a summation of infinitely narrow rectangles whose basis of dx shrinks toward 0, evaluated over a distance of ab. The smaller the rectangles, the better the approximation of the area. By making the rectangles infinitesimally narrow, then theoretically an exact value of the area is obtained at the limit. Just as in Newtonian classical differentiation, dx is never allowed to reach an exact value of 0, since to do so symbolically demands a computed area of 0. Once again, quick principles state that not only does h equal 0, but that it must obtain an exact value of 0 in order for f prime of x to obtain an exact value of the limit L. Quick principles posit that the area of any of these Newtonian rectangles is represented by base times height equals x plus h times f of x, where h is the distance between some two points. As h goes to 0, the area of the rectangle, x plus h times y, also goes to 0. The obtainment of h equals 0 results in the area of the rectangle obligatorily obtaining a value of x plus 0 times y equals xy equals 0. Please note that the convention of h goes to 0 is strictly a Newtonian concept. It is superfluous in quick integration. The quantity h must and does become 0. However, forcing h equals 0 leaves a remainder, the point x and its point y analog. This remainder of x and y results in several types of mathematical constructs, one of the most novel being that xy is the polar of pole x. In short, we decrease h until at 0, a equals a perp. In summary, quick integration forces h to a value of 0. When h equals 0, then the base of the rectangle equals 0. Only the height of the rectangle remains. This length is the line segment xy, or the polar x perp equals a perp. The height or side of the rectangle is y equals f of x, and x is the single point indicating where y equals f of x intercepts the x-axis. Therefore, the line segment is designated as yx equals f of x times x. Notice that there is no dx, only a definitive x. The ordered pair xy defines both a point and a line. This point-line duplex, by definition, must also represent a slope of y over x and a derivative f prime of x. The summation of y over x as points, and therefore the summation of derivatives, results in the formation of the curve f of x. The horizontal summation of y over x as lines, or polars, results in the computation of the area under the curve. The computation of the area under the curve may also be viewed as the summation of all the ordered pairs, which are points, which lie underneath the curve, since each and every ordered pair must be a slope and therefore a derivative. The Eulerian fundamental theorem of calculus may be expressed in a variety of different ways, since all trigonometric identities are equivalent. Here are some of those expressions. The fundamental theorem of calculus says differentiation and integration are reverse processes of one another. Here's a proof that proves that statement. Okay, we are finally ready to put quick to the test. Let's see how it stacks up against Leibnizian and Newtonian calculus. Mythology says that Newtonian calculus is pretty easy. All you have to do is remember these 6 derivatives and integrals, and you have pretty much conquered basic calculus. They are easy enough to remember, but actually understanding the proof of each of these using Newtonian principles may prove to be a bit challenging. So I'm not going to prove these using Newtonian principles. I'll leave that up to you. There are several proofs on the internet and in any basic book on calculus. But I will take this table and derive the same derivatives using quick, but with a bit of a twist. I'm going to slightly alter Mythology's version to this. Now the first thing we have to remember is that given the Eulerian fundamental theorem of calculus, integral and derivative are relative, since they are reverse processes of each other. One precess is left, the other precess is right. You choose which. So without using any algebra, we can figure out the derivative of a constant. A constant isn't changing. A derivative may be defined as the instantaneous rate of change. Since a constant isn't changing, there is 0 rate of change, so its derivative is 0. But we also know that when using the centroid method, that the ICR is formed at precisely the instant when there is no rate of change. At the ICR, the derivative and integral become indistinguishable. So at the ICR, we form a derivative that is a constant of 0. I have stated that all trigonometric identities are quaternions, and here's why. Even though we may not think of it as such, one is a trigonometric identity. The sine, cosine, and tangent may all be expressed as the ratio of 2 trigonometric identities, sine over 1, cosine over 1, and tangent over 1. That ratio makes them a slope, and therefore a derivative, and therefore a quaternion. The same holds true for their reciprocals, the cosecant, secant, and cotangent, respectively. Quick excels in computing the derivatives of the trigonometric identities by finding their limits. And none is more simple to prove than the derivative of the sine. In Quick, we find the derivative of a function by finding its conjugate, which is its limit. And to find the conjugate, we simply take the function to 0. For instance, a 100% absence of the North Pole ensures a 100% presence of its conjugate, the South Pole. And so to find the derivative of the sine, we simply rotate the sine from pi over 2 radians to 0 radians. Its Tovasian conjugate is the cosine, and we can see as the sine gets less and less, the cosine increases more and more, until when the sine is at precisely 0 radians, then the cosine is precisely 100% at 1. Now what is a Tovasian conjugate? We can think of Tovasian conjugates as right-angle opposites. For instance, the polar opposite or polar conjugate of the cosine is the versine. The Tovasian conjugate, or right-angle opposite of the cosine, is the sine. The derivative of e to the x is simply e to the x. Let's prove this. Here's a curve of e to the x. Let's find the value of e where e to the x equals e to the 1 equals e. We do this by simply advancing a distance of exactly 1 on the x-axis, giving us a precise y value of e. Notice that a right triangle is formed by the base of 1 and the height of e. The hypotenuse of this triangle has to be the slope, since the slope is equal to y over x, which is equal to e over 1, which is equal to e, which is equal to the height. And so the slope of e is e, which means the derivative of e is e. But what we discover is that if we keep the base at a constant of 1, we can slide this triangle up and down the x-axis in whatever direction we please, with it always being tangent to the curve. The height and slope adjust accordingly such that it may always maintain a singular tangent point. This means that no matter the value of e to the x, its height, which is y over x, which equals y over 1, will always be its slope. Therefore, the derivative of e to the x is e to the x. And by the Eulerian fundamental theorem of calculus, the integral of e to the x would also be e to the x. The Eulerian fundamental theorem of calculus also dictates that since at the ICR the derivative and integral become indistinguishable, then the area under the curve, which is the integral, simultaneously equals a tangent point on the curve, which is e to the x. So the derivative and integral of e to the x are equivalent, and both may be expressed as e to the x. The discussion of ln of n can get real tricky, so let's first start with the basics. F of x is equal to y equals e to the x. This means e taken to some power x yields a value of y, and x is the natural log. This is all pretty simple and straightforward. Conversely, we can use the natural log x to find the y value. The reverse process uses y to find the x value, and for that we use the ln notation, and that is given by ln of e to the x equals ln of y equals x. Now, by both Newtonian and Quickian tenets, we have proven that the derivative of the sine is equal to the cosine, and the derivative of the cosine is equal to the negative sine. So we know that these two equations must be true. Now, by Newtonian tenets, we are given that the derivative of ln of x is equal to 1 over x. This animation very nicely illustrates the relationship between the inverse functions ln of x and ln of y. These are inverse functions of e to the y and e to the x, respectively. And so we obtain this somewhat simple proof by simply taking the conjugate of e to the x and e to the y. And while I'm here, let me quickly derive the Quickian power rule of quaternions. If e is truly a quaternion, then e to the ln of y is equal to the ln of y times e. And so in general terms, q to the n equals nq, which is our Quickian power rule. Lastly, we come to the power rule of differentiation, perhaps the most fundamental of all calculus rules. Newtonian principles apply the binomial theorem to prove the power rule of differentiation. However, in Quick, we shall use another proof. But before I get to the Quickian proof, I should first introduce the Newtonian version of this proof. On the internet, I ran across a version of this proof from Prime Newtons. His proof has got to be one of my all-time favorites, right up there with the Basel problem and Gauss's summation of the integers 1 through 100. There is a degree of cleverness and conciseness that I find to be extremely satisfying when studying these proofs. I don't know if Prime Newtons discovered this proof or not, but I enthusiastically offer him my sincere congratulations. He starts with this basic set of equations. Anyway, I can't do it justice, so I'll just let Prime Newtons present it.
And this is where we begin. So, I'm going to say that if I take the derivative d dx of ln y will be equal to the derivative also d dx of n ln x. So, if I differentiate a natural log function, remember what I say? It's the derivative of the inside divided by the inside. So, the derivative of the inside is y prime divided by the inside over y. That's how you take the derivative of any natural log function. Okay, on the right-hand side, well, this is a constant. I'm differentiating with respect to x, so I can just keep the n. And what's the derivative of natural log of x? We know that it's 1 over x. Nice. So what is y prime? Well, y prime, if I multiply both sides by y, is going to be n times 1 over x times y. Watch this. This is the same thing as n. What did we say 1 over x is? It's x to the negative 1. That's how you write it when you're dealing with laws of exponents, right? And what is y? From the beginning, we said let y be x to the n. So times x to the n. Ladies and gentlemen, this is n times x raised to u. Add these two together, you get n minus 1. And what is y? We said y was x to the n, so this is what we want, x to the n prime. Never stop learning. Those who stop learning have stopped living. Bye-bye.
What an absolutely amazing proof. I'm so impressed by this proof that I'm going to borrow from it and present the Quickian version of it. My only restriction is that he used differentiation to prove a rule. I'm going to derive the rule to prove the differentiation. Now again, in Quick, we always make a distinction between x and y when dealing with the ln notation. So we are going to reinterpret his initial equations. Now let's reinterpret his derivation. And this, ladies and gentlemen, is the Eulerian expression of the fundamental theorem of algebra. Now you may ask, what is the fundamental theorem of algebra? Here's the formal definition for the fundamental theorem of algebra. And this is a simple definition of a polynomial. And this is a simple definition of a root. Now the fundamental theorem of algebra is just a fancy way of saying how many x-intercepts will a polynomial in x have. And the Eulerian fundamental theorem of algebra says it will have n number of roots given e to the n. Here's why. Descartes proved that any curve placed upon the Cartesian plane must have an accompanying equation. Quick says any curve placed upon the Cartesian plane can be placed upon the complex plane, and any curve placed upon the complex plane must have an accompanying Euler-Formula equation of a times the quantity cosine theta plus I sine theta. The Quickian power rule, q to the n equals nq, is a consolidation of de Moivre's formula. De Moivre's formula says that the quantity cosine q plus I sine q to the n power allows us to operate on the quantity cosine q plus I sine q n times. The quantity cosine nq plus I sine nq allows us to operate on the quantity cosine theta plus I sine theta once over an angle of nq. So by de Moivre's formula and the law of indices, we get a times e to the x is equivalent to the quantity cosine theta plus I sine theta to the a power, where in this case e to the x is the unit quaternion. Remember, e to the x is a quaternion, and all quaternions obey the law of indices. Now the way we find a root is by simply making y, or the sign, equal to 0. And so by Quick, we simply get a or n number of roots. thus the Eulerian fundamental theorem of algebra. Now earlier I stated that where prime Newtons use differentiation to derive the rule, that I would derive the rule to prove the differentiation. To start this process, we must state two crucial distinctions. The Newtonian power rule differentiates with respect to x. That is, by Quetekian tenets, it forces x to obtain a precise value of 0. Conversely, the Quetekian derivation of the Eulerian fundamental theorem of algebra does the exact opposite. It computes the conjugate or the antiderivative. It therefore differentiates with respect to y, and therefore forces y to obtain a precise value of 0 or to form a 0 root. And so to prove this antidifferentiation, let's pick up at this point in prime Newton's derivation of the power rule, where y prime over y is equal to n times 1 over x. And with a bit of algebraic rearrangement, we get this equation. The quantity x over y is a negative slope, or an antiderivative, or an integral. But 1 over y prime equals negative y prime, which is equivalent to x prime. Therefore we get x over y is equal to n times x prime. And so by the law of exponents, we get x over y is equal to x to the n prime. But prime Newtons and Johnson have already proven the Newtonian power rule. So therefore we may express the Eulerian fundamental theorem of algebra in terms of antidifferentiation. But both the derivative and antiderivative of e to the x is e to the x, since the point and area under a curve of e to the x are equivalent. Therefore we obtain this equation. Therefore, by deriving the Eulerian fundamental theorem of algebra in terms of x over y, we prove the differentiation of its conjugate y over x, which yields this equation. Therefore, we may express the full comprehensive expression of the Eulerian fundamental theorem of algebra. The Quetekian power rule allows us to solve the Fermat-Catalan Conjecture. The Fermat-Catalan Conjecture is essentially the Bill conjecture, which I solved earlier. If the natural logs 2, 3, and 5 are each taken to a power of 14, 4, and 8 respectively, then using the power rule of natural logs yields a final value of 40. Therefore, if 2, 3, and 5 equals a, b, and c respectively, and 14, 4, and 8 equals m, n, and k respectively, then we can easily solve the equation a to the m plus b to the n equals c to the k. It too would have a final value of 40. The question as to if there are finitely many solutions is proven via the law of indices. When m and n must either sum or produce a product that is equal to k, then the number of solutions cannot exceed k. So ostensibly there are finitely many solutions, but there is nothing that says k can't be infinitely large, in which case there can be infinitely many solutions. Therefore the Fermat-Catalan conjecture is false. This is a graph of 1 over x. If we draw any tangent to the curve, we form a right triangle whose hypotenuse is the tangent line. The area of the triangle is 2. We can do it for this tangent line, or this tangent line, or this tangent line, and the result is always the same. The area of the triangle will always be 2. Now the area of the triangle is very easy to compute. We simply multiply base times height and divide by 2. But this can also be the area of a rectangle if we so choose. So in order to maintain this area of 2, y must equal 2 over x, and x must equal x. But this would also mean that there is a constant slope of 2 accompanying this rectangle, which equivalently would be expressed as y equals 2x and x equals x, resulting in a slope of 2x over x. Every value of 1 over x results in a tangent point and therefore a tangent line, and is therefore a derivative. But we know that the area under a curve is an integral, so 2 is the integral for every value of 1 over x. But an integral is the summation of all its derivatives, which in this case means the summation of all unit fractions, including 1 over 1, must equal 2. But wait, it gets better. If the summation of all unit fractions is 2, then the summation of all unit fractions except 1 over 1 must equal 1. We take the reciprocal of both sides and get 1 equals the summation of all integers from 2 to infinity. Adding 1, we get the sum of all integers equals 2. Now I could stop here and call it a day, but this curve is the gift that just keeps on giving. So let's continue. So let's tackle Goldbach's conjecture. Goldbach's conjecture is one of the oldest unsolved problems in all of mathematics. It states that every even natural number greater than 2 is the sum of two prime numbers. So to begin, let's rewrite our slope formula. In this case, we will allow x and y to only be positive integers. So this would mean that 2x represents any and all of the positive even integers. Now, given y's position and the requirement that the slope must remain a constant of 2, then y is only divisible by 1 or itself. This is the definition of a prime. Therefore, all positive integers as quaternions are prime, and every even number must consist of at least two prime integers, since every even number must be x plus x equals 2x. Therefore, Goldbach's conjecture is true. I know, absolutely crazy, right? The Stroop effect is in full effect, but don't worry about it for now. We will circle back around to this later when we need it. And since we are here, then the solution to the twin prime conjecture follows axiomatically as a corollary, given that all the x's are prime and the existence of our 2x over x slope. And if Goldbach's conjecture and the twin prime conjecture are true, then the other two Landau problems are also true. And since we are dealing with 1 over x, let's make a quick detour over to the Erdos-Straus Conjecture. The conjecture essentially says that the number 4 over n can be written as the sum of 3 positive unit fractions. We can solve this conjecture very easily using Quick. Let's go back to when we derived the area of 4 triangle. Let's rearrange it so that it looks like this. Now, since every unit fraction can and must be composed of 2 other unit fractions, then we can convert 2 unit fractions into 1 unit fraction and solve the conjecture. And so the Erdos-Straus Conjecture is true. Still not convinced, huh? Okay, let's go to the other extreme. Here's my proof of the Erdos-Straus Conjecture based upon Euclid's formula. In Quick, we call the Pythagorean theorem the diagonal rule, which was first discovered by the Mesopotamians and Egyptians well over a millennium ago. In Quick, we also call the Pythagorean triple a diagonal triple. Weilberger gives us some fascinating lectures on the subject, along with the famous Plimpton 322 tablet in his math history lectures. Weilberger also informs us that the Mesopotamians even had their own version of Euclid's formula nicely compacted into this multiplication algorithm. So if we let AB equals 1 squared equals 1 and carry out the necessary algebra, we find that 1 equals AB, 1 over A equals B, and 1 over B equals A. Now, the purpose of all this was to establish that A and B can be represented as unit fractions or Egyptian fractions. And since they are unit fractions, we can equate the diagonal triple with sides A and B to the Egyptian fraction equation. Next, we substitute in A and B from the Mesopotamian algorithm into the Egyptian fraction formula. In doing the necessary algebra, we wind up with this equation. Now, Euclid's formula is a formula where if you are given a diagonal triple or Pythagorean triple, you can compute the lengths of the sides. So a diagonal triple of sides ABC would have A being the short side, B being the even long side, and C being the hypotenuse. So letting Euclid's formula be our guide, let's expand this into this. And so now we can rearrange this into this, which simplifies to this. Now, to find some integer n, we simply factor by n. And taking the reciprocal of both sides, we see that the Erdos-Straus conjecture is indeed true. And expressing it in terms of the derivative 1 over x, we arrive at this final result. And since 2 equals -1/2 in the area of 2, let's visit the Collatz conjecture. Here's another unsolved conjecture we will solve using the principles of Quick. And we find, doing the necessary algebra, that the solution to the Collatz conjecture is simply the summation of the simple geometric series whose first term is 1/2, which ultimately sums to 1. Therefore, the Collatz conjecture is true. Going in reverse, it's very easy to see that every term is a Fermatian integral of the preceding term. So 1/8 is a Fermatian integral consisting of 2 halves, each half being a 16th. But we can also prove this much more elegantly and beautifully by observing an equally elegant and beautiful animation of Nicolas's proof of divergence by your favorite TA. Here we see that no matter how finely we divide the curve into its unit fractions, we can always obtain a set that can and must converge to 1. And here he illustrates how summing unit fractions is no different than summing halves. And so Quaresme leaves us with this equation. Now this may or may not prove divergence, but that's not really our concern here. Our goal is to prove that by subtracting 1 from this equation, we can definitively prove it converges to 1. So let's do that. Let's subtract 1 from each of the 3 terms. Let's rearrange and name our terms so that they are more recognizable. Now the Collatz process essentially says keep making halves or summing halves, and eventually you will produce 2 aggregate halves whose sum equals 1. Quaresme actually proves this is true. Now why is this true? Well, we know that this geometric series is equal to 1. And so we simply get this. And so the Collatz process converges to 1 and is therefore true. And if we want to prove that the sum of all the unit fractions including 1 over 1 is equal to 2, then we simply add back the 1 we previously subtracted. Now what was the point of proving the Collatz conjecture? I used it as an indirect proof of Fermat's rule that plus or minus 1/2 is a derivative and therefore a slope. Later on we're going to need this fact. Now this is my original proof of the Riemann hypothesis. Well, today let's go over it in more detail. So first off, what is the Riemann hypothesis? The Riemann zeta function is an infinite series summation of reciprocals where each denominator is being raised to some power s. The summation of the terms on the right-hand side converge to form a limit. Conventionally, the exponent s may be any number except 1 in order to obtain a convergent value. But through the power of Quick, we have already proven that such a summation equals 2, so therefore zeta sub 1 equals 2. It is conventionally found that s, as any even negative number, will yield a value of 0. These derived zeros are called trivial zeros. There also exists a set of non-trivial zeros, and it's these types of zeros we are interested in. So the Riemann hypothesis essentially comes in 2 parts. Part 1 asks, what is the value of s when zeta sub s equals non-trivial 0? Part 2 proposes, prove that all non-trivial zeros are located along the critical line when zeta sub s equals non-trivial 0. Okay, now that we know what it is, let's solve it. Superimpose 2 unit circles. Now we superimpose these 2 circles because remember we began with area of 4 and reduced it by half into the area of 2. And this generated 2 Cartesian planes, one being the Argand diagram. Shrink one of the unit circles such that it is pinned between the origin and 0 radians. Label the larger circle the body centroid and the smaller circle the space centroid. This configuration of centroids automatically makes the y diameter of the space centroid the critical line. We construct triangle ABC where the base of triangle ABC is the critical line and where the apex of ABC is point B or 0 radians. The hypotenuse of triangle ABC coincides with the critical line, which is equal to I. Our earlier proof of the Collatz conjecture proves that I is indeed a slope and therefore a tangent. The midpoint of I is 0. Therefore, every point along the hypotenuse as tangent must also equal 0. These zeros are non-trivial zeros. Two applications of I on 1 yields -1. Therefore, I equals -0.5. Therefore, given the Riemann zeta function, when s equals 0, then -1/2, which equals -0.5, which equals I, equals non-trivial 0. But I can present an even more simple and more comprehensive proof that derives both the non-trivial zeros and trivial zeros. Conventionally, when y equals 0, then e to the x is undefined. We are told that there is no value of x that will yield a value of y equals 0, so the curve can never touch the x-axis. We can use the Riemann hypothesis to prove that when y equals 0, then x equals ±5 equals ±I equals ±2. And so we construct the space and body centroids just like we did in the first proof, and then apply the principles of e to the x equals y. When x equals 0, then e to the x equals e to the 0 equals 1 equals e to the I theta equals e to the I pi. So therefore I pi equals 0, which means I equals 0 over pi, which is equal to 0. This 0 is a non-trivial 0, but the entire y diameter of the space centroid is composed of non-trivial zeros. So I equals 0 equals y. Now when the entire y diameter, which is the critical line, is 0, then the left side of y becomes a negative root, and the right side becomes a positive root. And from this elegant proof, we can easily prove that when y equals 0, then given e to the x equals y, then e to the ± I equals e to the ±0.5 equals e squared equals the square root of e equals y equals 0. This says the instant y equals 0, then the y and x axes are interchanged. The e to the x curve is rotated pi/2 radians into the e to the y curve, and vice versa. In short, when y equals 0, then e to the x equals e to the I, and the unit quaternion operator I rotates his base scalar e pi/2 radians. These Aphasia conjugates can only exist upon the line of reflection, which must always have a slope of 1. Therefore, there is a 1-to-1 mapping of y to x, and they cannot vary. This is why these zeros or polynomial roots are prime and why the Goldbach Conjecture is true. And so we prove once again that when y equals precisely 0, then the derivative of e to the x is e to the y, and the derivative of e to the y is e to the x, and the derivative of e to the x is e to the x. But we encounter a semantics problem. If the critical line is the entire y-axis of the space centroid and equals -0.5 equals 2 equals non-trivial 0, then the conjugate x-axis is 0.5 equals -2 equals trivial 0. And as long as we define the critical line as being the line of reflection between e to the x equals y and e to the y equals x, then yes, all non-trivial zeros will and must be located upon the critical line. If the critical line is defined strictly as the y-axis of the space centroid, the non-trivial zeros are also found along the x-axis of the space centroid, as well as throughout the entirety of the 2-unit circles. Armed with our more comprehensive expression of the Riemann hypothesis, let's go back to the Goldbach conjecture and revisit all that craziness about all the positive integers being primes. As things stand, we know that this should not be the case because every even number will have at least 2 divisors, 2 1/2 of itself. So it fails the definition of a prime in that respect, but it obeys it by virtue of being a natural log and a quaternion. We prove that this must be the case in the area of 2 rectangle, where all positive integers, as quaternions or natural logs, must be prime by definition. We also prove this must be the case once we establish the line of reflection, and thus the ICR, that must always exist between e to the x and e to the y. Again, let's revisit the hexagon video of the switching exponential curves. When x equals 0, e to the x is obligatorily rotated pi/2 radians into e to the y. That line of reflection is a slope of 1, and that slope of 1 is maintained by the addition of x plus y, where x and y must always be equal, thus creating a slope of 1 and thereby satisfying the definition of a prime, where x and y can only be divisible by 1 in itself in order to maintain a slope of 1. So the existence of the QECian prime has been well proven and established. But we have yet to account for the exclusivity of the fundamental theorem of arithmetic prime. Why are 8 or 25 or 63 primes under QECian tenets, but not primes under the fundamental theorem of arithmetic tenets? We have now established enough background information to precisely answer that question. But before I get started, let me make two distinctions between two types of additions. Suppose we were asked, what does 3 plus 4 equal? Most people would immediately say the answer is 3 plus 4 equals 7. This we will call arithmetical addition or scalar addition. But it is just as legitimate to state 3 plus 4 equals 5 if we are adding sides in a right triangle or adding orthogonally. This type of addition we will call linear addition or vector addition. Now, when dealing with the curve of 1 over x, we also encountered an inherent slope or equivalent area of 2, similar to that encountered when dealing with the dual e to the x and e to the y curves that generated an inherent slope of 1. This shouldn't be too surprising since the derivative of ln of x equals 1 over x, and ln of x equals ln of e to the y equals y. But where did this area of 2 and its accompanying slope come from? This is a graph of the inverse curves of e to the x and e to the y. It includes their line of reflection, which must have a slope of 1, where x equals y, and the slope is 1 equals y over x equals x over x. Again, this renders all such x and y's primes. This is a graph of 1 over x, and it must have a slope of 2. The slope of 1 equals x over x is, and must be, common to both curves. This is a QECian curve of the e to the x over e to the y line of reflection that illustrates this relationship between the two curves. Included in the illustration is the QECian number line. The QECian curve illustrates how the arithmetical addition of primes form all the even numbers. It also shows us that every even integer is also formed as an x squared equals 2x number. For instance, 6 is formed at the corner of a 3 by 3 square. The arithmetical sum of 3 by 3 is 6. By the law of exponents, this is allowed. This is also dictated by the QECian number line. And so we are now ready to precisely answer where and how the fundamental theorem of arithmetic primes are formed. The sine and sagitta are necessarily the x and y components of the line of reflection, since x must equal y. The arithmetical sum of the sine and sagitta as exponents is exactly equal to their linear sum. And so by the law of exponents, we present the following equations. The arithmetical sum forms the QECian prime or ICR. It is placed directly upon the line of reflection, which must always possess a slope of 1. The linear sum forms a slope, whose midpoint is the arithmetical sum. Equivalently, the sum of the cosine plus versine must always equal 1, in this case 1 being the line of reflection. They must obligatorily sum arithmetically, and they must also obey the same rules of summation as those obeyed by the sine and sagitta. That is, they must sum arithmetically as primes. And it is because of this interaction between the cosine and versine that the fundamental theorem of arithmetic primes are formed. These primes can only be divisible by one of themselves, but this inherent primeness is not due to any occupation of the line of reflection, but rather due to the disposition of their x and y components as they form the resultant slope. And just as the number line bears out, along the line of reflection the even integers are all squares, and the odds are their differences. Having now answered the where and why of the fundamental theorem of arithmetic prime formation, we may now answer why the area of 2 or area of I exists. In a 3-4-5 diagonal triple, the ordered pair 3, 4i constitutes a complex number whose value is their linear sum 5, with 5 being the hypotenuse of a diagonal triple formed by the odd 3 and even 4 sides. Thus the linear expression of 3 plus 4 equals 5. This is governed by Euclid's formula. Given the primes 3 and 5, we may generate two equivalent equations. And so arithmetically, we get the expected result of 3 plus 5 equals 8. Linearly, we get the unexpected result of 3 plus 5 equals 17. The quantity 3 plus 5 equals 17 is called a QECian triple. It is the linear equivalent to an arithmetical summation of the form x squared equals x by x, which is equivalent to 2 times x, which equals x plus x, which must obey Bow's fourth law. We also discover a type of exponential or Eulerian quadrants. We have established that quadrants is squared length. Thus, 5 squared may be 5 square feet or 25 linear feet. But the QECian number line and QECian power rule says that squaring any integer is equivalent to doubling that integer. So therefore, 5 squared may also mean 25 linear feet or 10 linear feet. Using our QECian Triple, we can now find the perfect Euler's brick. Here we have an image of an Euler's brick. Using our QECian Triple, we are given the following natural log summations. We allow a equals 3, b equals 5, and c equals 7. We therefore obtain the following 3 equations. Since 3, 5, and 7 are natural logs, then by the power rule of natural logs, we obtain this set of 3 equations. From the QECian number line of reflection, then it must be the case that 34 is the length of the diagonal of a 17 by 17 square. It therefore acts as a quadrant. The space diagonal is given as a squared plus b squared plus c squared equals g squared. Previously, we were given this set of 3 equations. Therefore, d squared plus c squared equals g squared. Given this set of 3 equations, we insert the appropriate values and obtain a value for the space diagonal, where d squared equals 34, c squared equals 49, and d squared plus c squared equals 83, which is the length of the space diagonal. Note that the dimensions d squared, e squared, f squared, and g squared are all quadrances and may therefore act as lengths. Therefore, through the use of the QECian Triple, we derive a perfect cuboid or a perfect Euler's brick. This perfect Euler's brick has dimensions in quadrances, and these quadrances are given as d squared equals 34, e squared equals 58, f squared equals 74, and the space diagonal equals 83. But just to make sure, let's double check our results. The space diagonal will form the hypotenuse of a right triangle AFG. This would yield a diagonal triple of a squared plus f squared equals g squared. We therefore derive the following diagonal triple. And in deriving this diagonal triple, we therefore establish the distinction between the QECian triple and the diagonal triple. The QECian triple 3 plus 5 equals 17 produces an even quadrant. The diagonal triple 3 squared plus 37 squared equals 83 produces an odd quadrant. We therefore prove both the existence and utility of the QECian triple. I stated earlier that the Eulerian fundamental theorem of algebra produces a different prime than does the fundamental theorem of arithmetic. Let's explore this a bit further. Let's revisit the Eulerian definite integral. We describe such an integral as the summation of all polars spanning h with the addition of an endpoint polar. This presents as x plus h. We also prove that such a polar is a derivative because, as the remaining side of a rectangle, it is necessarily a rate of y over x. In a polynomial, when we force y to 0, we are essentially forcing y, the polar, to assume its pole form, the x-intercept x. But big A equals little a perp, and little a equals big A perp, so x and y as pole and polar become indistinguishable. But in the definite integral, the lone side polar can only exist as the rate y over x. And since y and x are indistinguishable from each other, then they can only be divisible by one or themselves in order to maintain polar pole status or rate derivative status. This is the definition of a prime, and so all root poles are prime. And so once again we prove Goldbach's conjecture is true. We also present the QECian spiral. Its qualifying characteristic is that by maintaining a constant base of 1 for all the right triangles in the spiral, then all other sides are simultaneously both height and hypotenuse, which we have defined as always being a slope. The only other quaternions that display this unique characteristic are the radian versors E, V, and Chi. This is why the e to the x of the Eulerian fundamental theorem of algebra produces root primes or QECian primes. But also note that these hypotenuses must also be both even and odd, since they are both the even height and odd hypotenuse of a right triangle. This is precisely a description of the e to the x, e to the y line of reflection. The QECian spiral is also the genesis of the QECian triple, since it allows for even hypotenuses. Lastly, it becomes clear why the fundamental theorem of arithmetic primes form a spiral pattern. It is because they simply do and must occupy the QECian spiral. In the unit circle, even though E and I predominate as irrational operators that produce irrational products in the form of the sine and cosine functions, it nonetheless still must also produce rational products as well. And it does this through the use of rational analogues like irrational I equals 2 and irrational E equals 1. So what is the rational analog of pi? Well, that's easy, but not so obvious. It's plus or minus 1 depending on the direction of I's rotation. So pi is equivalent to an absolute value of 1. Therefore, the full circumference of the unit circle is 2 pi, which must sum to 2. But Riemann says that the sum of all the positive integers equals -1 over 12. Let's see what Euler has to say on the subject by taking a look at his proof of the Basel problem. Here is the Basel problem. This ostensibly poses a big problem for us because we have definitively proven through the area of 2 and Erasmus' proof of convergence that the sum of the unit fractions, including 1 over 1, is equal to 2. And so the Basel problem would simply yield 4. But here's the difference. Euler's Basel problem is the summation of radians in the form of the sine and is indeed correct. Johnson's Basel problem is the summation of areas or quadrances, and it too is indeed correct. Therefore, pi squared equals 24. But pi is a quaternion and therefore must obey the law of indices. So we get a final answer of pi is equivalent to 12, which is equal to -1 over 12. Riemann summation differs from the expected result by a factor of 2. How do we account for that? Well, quick sums QECian primes, and these primes comprise the QECian spiral. Note the difference between the QECian spiral and the Pythagorean spiral. The square root integer adds linearly, just like the QECian prime integer adds arithmetically. And so if Riemann took his measurements within the Pythagorean spiral or within the space centroid instead of the body centroid, then he would compute the sum of all the positive integers to be -1 over 12, which equals 12. However, in any case, be the measurement taken within the space or body centroids, pi may be represented rationally as the integer 12. Now, of course, we invite the predictable response of, that's numerology. And so for all the doubters, I'll leave you with this intriguing proof I ran across on Numberphile presented by Matt Parker. The following proof was actually given by one of his colleagues in response to one of his own. And so we are gifted with another clever, concise proof. Now let's see what this means when we apply QECian tenets. We are given that 1 plus phi equals phi squared. Therefore, phi squared minus 1 equals phi. We immediately see that the prime squared minus 1 is the height or quadrants of the phi to the x triangle. Therefore, if phi squared minus 1 equals phi, then we obtain the following equation. And so a prime is produced with every phi-based revolution of the unit circle. And so we see that phi is responsible for the rational periodicity of the rational fundamental theorem of arithmetic primes. But we have paid little attention to the implications of phi to the x and e to the x being equivalent. If they are equivalent, then phi to the x must have an accompanying conjugate equivalent to e to the y. And it does. The conjugate of big phi to the x is small phi to the x, and small phi to the x equals a -0.618. But xyz is fully equivalent to ijk. So if e and phi correspond to x and y, then there must be a remaining z equal k analog. This analog must be a constant of nature, and is hereby named Christopher's constant, and is represented by the Greek letter chi. We can actually prove the existence of chi trigonometrically. Given 1 plus phi equals phi squared and the e to the x triangle, then we know that phi must be located somewhere along the e to the x height. E to the 0 equals 1 as tangent is fully proportional to e to the x equals y, which is the height, which is also equal to the tangent. So phi sub 0 must obligatorily be located at some point along the x equals e to the 0 axis. This would then divide the x equals e to the 0 axis into two scalar trigonometric identities, the cosine and versine. But trigonometrically, we see that the versine is divided into two sections. This therefore demands the presence of a third scalar. This third scalar is chi. It is clear there are three classes of Quaternion rotators. Therefore, E equals phi chi is the scalar form of I equals jk, and corresponds to the previously mentioned special ratios of cosine to versine, cosine to cotangent, and cotangent to versine. And from this table we see that B is the rational analog of e to the x and phi to the x. Now I've stated that there is no infinity in QEC, and yet I used it in this summation. That's because I have not developed any symbolism exclusively for QEC and must rely on the current conventional symbols. In QEC we may divide any object infinitely. That is, we may divide it to whatever degree we wish, but the division will and must ultimately end. There is no infinity. There are no infinitesimals. There is no dy or dx. In QEC we do not hover about a point. We get there with pinpoint accuracy. But that also means in QEC that we do not use the partial, particularly nabla. The nabla is used extensively in physics to compute physical quantities in 3 dimensions. Well, in QEC, the 3-dimensional coordinates of x, y, z are equivalent to the quaternions I, j, k, which equals -1. So volume is equivalent to -1 in QEC. Also, the physical quantity entropy is defined as energy per volume or force per area or pressure. And if volume is -1, then we can interpret negative energy as being energy per volume. By computing these physical quantities, we can dispense with nabla. However, the most efficient and transparent method of computing physical quantities in a 3D space is through the use of these gyrodynamic cylindrical components of acceleration. All physical particles are composed of quaternions, and any quaternion that moves, or doesn't move for that matter, must obey some aspect of these components. These cylindrical components of acceleration supply us with all forms of forces being exerted on or by an object. Here's the QECian Gyroscopic Force Theory interpretation of the forces. Let's start with Coulomb's law. Coulomb's law is exactly the same, except it deconstructs Coulomb's constant K into its two component parts. Those two parts are c, which is the speed of light, and r, or resistance, which is Coulomb's constant. Coulomb's constant has a value of 30 ohms. Coulomb's law of magnetostatics is almost exactly the same as Coulomb's law of electrostatics. The only difference is that in the static law, the charges remain at rest. In the magnetic law, they move. And so to each charge, we have to impart a velocity. And we do that simply by multiplying both sides by 1, or v squared over v squared. One of the velocities cancel out with the velocities in Coulomb's constant, and we are left with a constant of r over c, which must and does equal Coulomb's magnetostatic constant. Now the mass forces act in exactly the same way as the charge forces act. When two masses are static, we get Newton's gravitational force law. And just as we did in Coulomb's law, in QEC and my gyroscopic force theory, we break down the gravitational constant g into its two component parts. This we call Daniel's constant. And substituting Daniel's constant for g gives us Michael's law. Now again, Newton's gravitational force law and Michael's law are exactly the same. Now the magnetic version for both Newtonian gravitation and QEC is simply Newton's second law, where F equals the change in momentum. But QEC and the G of T also derives the Johnson senior law, where F equals the change in mass times the speed of light. Finally, if we factor Michael's law by 1, or v squared over v squared, we get this equation, and this equation. And so we derive 4 different expressions of the gravitomagnetic force. Notice that these two equations are the same force. You can't distinguish one from the other. This is one of the advantages of using Michael's law instead of Newton's gravitational force law, because Michael's law essentially unifies electromagnetism and gravity. It makes charge and mass fungible, and as we established in the solution to the Erdos-Straus Conjecture, 4 is an actual constant of nature. In quick, we use an alternative expression of the gravitational force called Scherl's law. And this we can expand into the GFT version of Newton's gravitational force law. And this we can expand into Johnson's law of magnetogravitics. Now all we did was take two velocities from c cubed and applied them to our two masses. It is still Michael's law or Newton's gravitational force law, but we have now expressed it magnetically. And so we can now derive Mackenzie's magnetogravitic constant, or the dark mass constant, var gamma. Var gamma is the magnetic analog of Daniel's constant, and from this we can derive the force equation for dark matter. This is Ajani's law of dark matter, and as you can see, there is no dark matter per se, just a hidden gravitational effect that occurs when mass moves. In fact, if we use Daniel's constant instead of Newton's gravitational force constant g, we can plainly see it is truly a magnetic effect due to moving mass. Now to add credence to our derivation, let's see what Sabine Hossenfelder has to say on the subject, and that should sufficiently prove my case for dark matter.
The other way to explain flat rotation curves is to say that if you go to the far out reaches of a galaxy, then the gravitational force doesn't drop with the usual 1 over r squared, but just with 1 over r. This leads to flat rotation curves, and this is the idea of modified Newtonian dynamics, MOND for short.
This is the fine structure constant. Up until now, no one could definitively say where it came from. Let's explore this a bit further. Newton's constant g, or more specifically Daniel's constant, is given as follows, but we also established that Crew's constant is equivalent to Coulomb's constant. Therefore, we obtain the following equation, which leads us to this equation. Therefore, we obtain the ratio of the gravitational force to the electrostatic force. This is called Courtney's constant. Conversely, the ratio of the electrostatic force to the gravitational force would be 4.6 times 10 to the 51. We therefore obtain this equation, which also yields this final solution, from which we may derive an alternative expression of the dark matter constant. And from this dark matter constant, we may derive several leptons. And from this list, we may consider lepton D of mass 1.82 times 10 to the 51 mega electron volts as being dark matter. Note that such a lepton is the size of a planet, indicating that the size of planets are neither random nor haphazard. Therefore, the dark force and the dark energy would be given by the following two equations. And since we have derived the mass of lepton D, we can derive an alternative expression of Mackenzie's constant, which is 2.22 times 10 to the 16 meters per mass. Now let me stop you here and give you a chance to catch your breath. Either your head is spinning from all the new concepts you've been introduced to, or you have simply dismissed much of what I've had to say due to the Stroop Effect, which brings us back full circle to Fermat's last theorem. I'm going to share with you one of the greatest proofs ever. And I say this because this proof introduces us to a whole new realm of mathematics, starting with Johnson's law of quadrances. Now, since the Stroop Effect wouldn't allow you to accept this equation, let's try proving Johnson's theorem one last time using Euclid's formula. We start with a 3-4-5 diagonal triple or Pythagorean triple, and applying the diagonal rule or the Pythagorean theorem yields 3 squared plus 4 squared equals 5 squared equals 25. But we also know that there exists a 7-24-25 diagonal triple, and so we get this equation. And applying the diagonal rule again, we get this equation. Now at this point, no one should have any problems with this computation. It's just standard algebra. But we squared the 5 squared just like it was a single side. It seems logical that we should also be able to square 3 squared and 4 squared as well. So let's see if we can by using Euclid's formula. Euclid's formula is a fundamental formula for calculating the size of a Pythagorean triple or diagonal triple. Since 25 equals 5 squared served as a single side in the 7-24-25 Pythagorean triple and is being squared as such, then using Euclid's formula, we may also consider 3 squared and 4 squared as being individual sides in a right triangle. which would give us this. But this looks wrong because 3 to the 4th plus 4 to the 4th doesn't equal 5 to the 4th. But let's just follow through with the algebra. To verify this Euclidean operation, we allow 4 and 3 to be expressed as the Euclidean 4 equals m and 3 equals n. And so if we are to square 3 squared and 4 squared, then using Euclid's formula, we get this. Now so far we don't know if it's true or not, but let's just still carry on with the algebra. And so we get this. And expanding this term, we get this term. We then substitute the expanded term back into the equation, and we get this. The 2 plus or minus 24 squared terms cancel, leaving us with our final answer. 3 to the 4th plus 4 to the 4th equals 5 to the 4th equals 25 squared equals 7 squared plus 24 squared. Therefore, Johnson's theorem is true. In this video, I have provided for you the Rosetta Stone of math and physics. The ball is now in your court. Good math, my friends.